All right, let us begin. This video is the most important video of this entire module, okay, of this entire unit. It's introduction to what we're going to talk about with sampling distribution. So sampling distributions usually trip a lot of people up. So going to go slow, going to talk about a lot of cool things because it's really exciting. It's really fascinating, but this is kind of where the stats starts to go a little bananas. Okay, so strap yourselves in, ask questions as you get them, and let's see what's going on. So there's a worksheet, the notes here. There's a bunch of good questions here. I'm not going to address these like I normally do. Okay. Instead, I'm going to talk about a bunch of things and introduce a lot of concepts, and then I want you to fill these in. And you may have to go back and rewind the video to get all of the answers. Okay. But that's where we're going to start with today. So we're actually going to use this website. And this website shows a lot of cool things. This website is linked at the bottom of the module. You can play with it yourself. It is fun to play with. I've played with this a lot on my own as well. And so let's just look at a couple things in general. Let's start by looking up here. All right. Looking up here at the parent population. So this is a normal distribution. Okay. So let's say we're looking at, let's get some hard specifics. Let's say we're looking at some SBSCC students, and we're saying, what's your favorite number? What's your favorite number between 0 and 32? And then for some reason, SBSCC students really like 16, right? So normally distributed to the middle. It wouldn't actually be normally distributed, but let's pretend, okay? Let's pretend that everyone loves number 16. And then the further away you get from 16, the less happy people are with it. And almost nobody is choosing 32 and almost nobody is choosing 0, all right? So on average, average number over here is the mean, and since it's normally distributed, the mean and the median are the same thing. All right, and it turns out that the standard deviation is about 5. So if something's normally distributed, that means about 68% of the data is within one standard deviation of the mean. So the mean can be seen right here. So within one standard deviation to the right and with one standard deviation to the left, that's about 68% of the data right here for this normally distributed model. Okay. So now let's say next that I want to take some samples. Okay. Specifically, I want to take some samples. I'm going to take a sample of 25 SBSCC students and say, what's your favorite number? I'm going to randomly do a simple random sample. So I'm just going to randomly choose 25 students and ask them what their favorite number is. And again, in this pretend situation, their favorite numbers are normally distributed, centering on 16. So watch what happens here. We're going to use this little thing, and I'm going to generate a random sample. All right, so one person picked over here, 4 people are picking over here. There's a lot of these are each block that's falling represents somebody that I'm asking from the population. Okay, somebody, I did a sample of 25 students just now, really quick, I know. I asked 25 students their favorite number, and I drew from the population. So we would expect with 25 students that, the sample mean would hopefully be pretty close to the population mean. The sample mean, the average of all of these 25 students, again, each one of these blocks represents a student. So this student said they liked 28 the most. This student said they liked, 22 or something the most. These 4 students said they liked 17. Only one person actually liked 16, if I'm counting right. And then like 5 students, this is 3, right? And then 4 students liked 15, 4 liked 14, and so on, right? So each one of these blocks represents a student that answered. Sample size of 25, and we can look at the sample mean. So the population mean is 16. The population mean is the mean of this parent distribution, the population. distribution. Okay, but our sample is not always going to be 16. Actually, in this case, our sample looks like it was about 15, our sample mean. Right, every time I take a sample, every time I take a simple random sample, I'm going to get different answers. Right, it's random. Every time I take a sample, I'm going to get a different average favorite number. Now, hopefully this average, which again can be visualized by this blue thing, hopefully this average of my sample is similar to the average of my population. That's the whole point of sampling. We want to know the population mean sometimes, but we can't ask literally everybody. That would be a census, and we can't always do that. So we do other kinds of sampling. So hopefully these are similar. So I'm going to ask 25 more SPSCC students. So again, what's going to happen? Oops. We just eliminated everyone that half the people that liked 14 and 15. Just went kind of Thanos on them. All right, I think this is about here, and this is about here. Kind of like this. All right, it's close to what it used to be. All right, it's close. It's close. We could just reset it. All right, so again, I'm asking 25 more people. And again, we're pulling from this distribution. So this time, in this 25 people, there's not a lot of people in the middle. This is a kind of a rare occasion, right? Most people we'd expect to be within 1 standard deviation of the mean. But this time we got a couple of these weird people, or different people, unusual people who have, you know, bigger favorite numbers and some with smaller favorite numbers. But again, the mean is still pretty close to what it should be. The mean here looks like it was like 14 or something. Let's take another sample. Every time we take a sample, again, I'm asking 25 more random SPSCC students. Every time I take a sample, it's going to have a different mean. Oh, the mean was way bigger this time, right? We didn't have any of these small numbers here. There was a lot of people from over here. And so let's just keep asking. I'm going to keep asking random groups of 25 people. And every time I do that, this blue thing, this sample mean, we're going to add a new blue bar, another sample mean. Ask another 25 students. Oh, 8, 12, 16, 14, 13. Oh my word, there's a lot of people that like this number. And there's another sample mean. And we could do this forever. So something that is going to kind of come into play, something that's going to be a topic that we're thinking about. Oh, this is a pretty big sample mean. As we go on with things, is how does this blue distribution look like? How do these means behave? Because if every time I ask, every time I take a sample, there's a different mean, the mean itself is a random variable. So we're going to another layer. We're adding another layer of mathematics, right? We have a population distribution up here, probability distribution of our population. And we also have a distribution of the means of sampling. That's what a sampling distribution is. It's saying every time I take a random sample, that's a random variable too. Let me say that again. Every time I take a random sample, the average number from that random sample will also be random. And that's what we're looking at today. This is really useful when we start talking about confidence intervals. This is really useful when we start talking about hypothesis testing, which is really kind of a cool trick and is related to a lot of stuff with my old job in slot machines. And that's kind of what we're doing here. So let's just introduce this a little bit more and do a little bit more exploration. Let's go faster, right? It takes a long time to individually choose these 25 people. So you can use this button over here and we can do 5 samples at a time. 5 samples of 25 SPSCC students. And each one of these samples will have a mean, a sample mean. So we should be adding 5 blue boxes to our distribution of means. 5 more boxes, 5 more boxes, 5 more boxes, 5 more boxes. And as we keep adding, I'm going to keep clicking, keep adding 5 more boxes. Look what's happening. The mean of our means, the mean of all of our sample means, and I know that sounds wacky, the mean of all of our sample means, because the blue represents our sample means, is about 14.65. The median of all of our sample means is about 6. The standard deviation is about 4.87. Compare those with our population distribution. Every SPSCC student. Kind of similar. Let's keep doing it more. Keep doing it more. I'm clicking pretty fast now. Keep on adding 5 more samples, 5 more samples, 5 more random samples with every click here. The mean is really close to 16 now. The median is still 16. Standard deviation got way smaller though, right? Originally, the standard deviation used to be kind of close to 5. Now it's getting smaller. Let's speed things up a bit. Let's click on 10,000. Let's take 10,000 samples. Ask 25 random SPSCC students their favorite number and find out what their average favorite number is. And we're doing that 10,000 times. Click. Whoa. Click again, click again, click again. It's not changing anymore. This is very closely related to the actual distribution of these sample means. The mean, almost identical. Median, almost identical. Standard deviation is about 1/5 of this standard deviation. Is that a coincidence? Let's keep adding more. Keep adding more. Standard deviation is almost is basically exactly 1/5 of this standard deviation. We're going to talk about why that is. A relationship between various things here. Okay? So let's do another comparison. Let's look at what if the distribution's not what if it's not normally distributed? Okay? What if we aren't normally distributed? Let's say, what if we have skewed data? Maybe we're asking people their favorite, I don't know, their favorite number again. I'm not very creative. But now we're not asking SPSCC students. Maybe now we're asking faculty members. And SPSCC faculty members, maybe their favorite numbers, they like small numbers because we don't like to work. Or something like that. Okay. Let's look at skewed data. So again, but now let's look at 2 different things. So now our population has skewed data. We're still going to look at the means, but now let's look at 2 different samples. What if we take a sample of 2 SPSCC professors and figure out what their average favorite number is? And also 25. So every time we take a sample, we're going to take a sample of 2 random ones and 25 random ones and see how those means behave. So again, 2 random professors, does that mean 25 random professors are going to have this mean that's going to pop down here. Again, let's do it again. 2 random professors, how does that mean? 25 random professors are going to have a different mean that we're going to put down here. Now, what do you think is going to kind of be some of the differences between these 2 things? Right? If we're only asking 2 random professors, it should be a lot more random, a lot more variability in these averages. But if we're asking 25, then that's a lot more people. The average, you'd think, would be more consistent. Right? The more people you ask, the more consistent the answers should be when we take a sample. Right? If I ask like 2 people what their favorite number is, you'd expect a lot more randomness in that average than if I asked 500 people what their favorite number was. So let's do that. Let's do this 5 more times. 5 more times. 5 more times. We're seeing that, right? When we're only asking 2 professors, the averages are kind of everywhere. But if we're asking 25 professors, the averages in their answers are much closer. Again, all of these blue blocks represent averages. Up here is asking 2 people. Up here is asking 25 people. Let's do a whole bunch of this. 5, 5, 5, 5, 5. A bunch of 5s. Let's see how this behaves. Click, 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 click. You can see, yes, when we're only asking 2 professors, there's a lot more variability, right? There's a way different number of averages. Also, look at the shape. Not just how spread out it is. Look at the shape. This thing down here, it kind of looks like a bell curve. This thing over here, I don't really know what this looks like. It's jaggedy. It's maybe still unimodal, right? There's maybe it's kind of leading to a peak around here, but there's some holes. Who knows? Let's click that 10,000 button. Let's take this sample. Ask 2 professors, find the average. Ask 25 professors, find the average. Let's do that 10,000 times. Oh. 10,000 more, 10,000 more, 10,000 more, 10,000 more. Really interesting now what's going on. Again, down here, this looks like a normal distribution. We can like put a little, like we can get pretty close to a normal distribution, but if we try to fit this one normal, this top one's not a normal distribution. This top one is skewed. It's skewed to the right. The tail is on the right. It's not symmetric. Normal distributions are symmetric around the mean. This one up here, though, is skewed. Well, you can also see the population is skewed. There's a connection there. Let's look at their means. The population has an average favorite number of about 8 for SPSCC professors. Again, this is made up data. Favorite numbers do not behave like this, but whatever. In our example, it is. If we asked 2 professors their favorite number and found the average is very close. It's almost the same average. And if we ask 25 professors, it is the same average. Median. It's 7 up here. It's 8 here. And it's 8 here. So the medians are really far off. The median is this pink line. Median is the 50th percentile. Equal number of data lies on either side of the median. Here, the median is exactly the same as the mean. Well, not exactly, very close. Here, the median is very, very, very close to the mean as well. So there's something going on with the medians. Standard deviation. In our last example, the first example, with the students' favorite numbers, the standard deviation was about 1/5 down here. Well, here it's 6.2 and here it's 4.3. That's not 1/5. Here it's 6.2, 6.2 and 1.2. Well, that is about 1/5. What's the relationship between the standard deviation? These are all things to be thinking about. But certainly, the more people we ask, n equals 25, going to have a smaller standard deviation in their averages than the fewer, October, don't stand on that, than the fewer people we ask. Okay? So, lots of topics to think about, lots of things to look at, and that's the introduction. All right, I want to do a really long introduction to kind of show where these concepts are coming from. Okay? The last thing we want to do in this video is I want to introduce the central limit theorem. Okay? So let's do it. Central limit theorem. So again, answer these questions on your own. Maybe you have to rewind the video. Again, if you only watch this video and watch it 5 times, that's probably better than watching every video once. Maybe. Okay, because this is the most important conceptual video here. So the central limit theorem is a really, really famous theorem in statistics, and we're not going to talk about it too much, but just a little bit. And the central limit theorem says the mean of a random sample is a random variable whose sampling distribution can be approximated by a normal model. Okay, depending on who you are, that may or may not have made any sense whatsoever. Because basically every single definition, every single word in here is like a full definition from something that we've talked about already in this class. The mean, right? The mean of a, here, let's go out of this mode. The mean, right? That's the average. That's our X bar, the mean of a random sample. Random sample, right? That's something we also talked about. Random sample is asking random people from the population, and it's going to be random. Specifically, it's a random variable. A random variable is something that we don't know what it equals. It's a variable, but it's random. We don't know what it equals yet. And random variables have things like probabilities and expectations and standard deviations and stuff like that. Okay, probability distributions. Sampling distribution, that's the new one, right? That's our blue graph that we did in the other thing. Can be approximated by a normal model. That's what we talked about in Unit 5. The normal model has a mean, has a standard deviation, had that 68, 97, 99.7, 68, 95, 99.7% rule, right? Where 68% is within 1 standard deviation, 95% approximately is with within 2 standard deviations in the mean, and so on. Okay, so this blue graph can be applied. This blue graph, and I keep thinking I'm saying bluegrass. This blue graph, right? That we, this blue graph down here can be approximated with a normal model. Okay, yeah, this looks like a normal curve. Blue graph can be approximated by a normal model, and the larger the sample, the better the approximation is going to be. N equals 2, that's a small sample size. This is kind of skewed. The normal model should be symmetric. But we made the sample size bigger. The bigger the sample size, the better the approximation will be. We made the sample size bigger, and yet, yeah, now it really looks like a normal curve. Okay, so lots to unpack here. And we have some requirements. So we're going to require that everything's independent. That's a pretty common requirement for a lot of what we're doing. Samples need to be randomly done. Okay, that's our randomization condition. And finally, there's a sample size condition. So this kind of only works if n, again, here n was 2. Here n was 25. It only really works if n is big enough. And it's kind of vague. It's case by case basis. But if something is normal, we don't really need that requirement anymore. But if something's really skewed, then we do have that sample size requirement. We saw that a little bit, right? If we look at, right, if we do the same thing, compare a sample size of 2 and compare a sample size of 25, and again, we did this 700,000 times, notice that this is still normal. So if our parent population is normal, there's no sample size requirement. That's what this is saying right here. If our population is normal, there's no sample size requirement. And you can see that because, yes, we still have a normal curve in our sample means. Now, this normal curve has a much bigger standard deviation. We'll talk about that in the next video. But they're both normal curves. They both have the same mean, same median, very different standard deviation. talk about that in the next video. So welcome to sampling distributions, means of means. Please reach out if you have questions.